So now that we know how three-phase systems look like, let's look at the practical constructions of three-phase generators. So now when you have a three-phase generator, remember you want it to produce for you the three phases that we've talked about just now. And in order for us to do that, the practical three-phase generators are called synchronous AC generators. The reason why they are called synchronous will be apparent shortly, but AC, we know what AC means, and for purposes of this discussion, we will be looking at three-phase generators, of course. So as with all electrical machines, it has a couple of parts. This, which is the entire compartment that holds it, is the frame. That is the metallic element that holds together the entire machine. Within the frame, you have bearings, two sets of bearings, one at each side, here and here. The bearings allow the rotating part of the machine to rotate freely inside the machine. The bearings are the only moving parts within the electrical machines. The stator, which is here, houses things that we call armature windings, which are mounted onto the frame. These do not rotate, they are fixed. And it is the armature windings from which you take off power. And that is mounted on the stator. The stator is the set of windings that is stationary. In the case of the generator, those two concepts are the same, stator and armature. They represent the same windings, but that might not be necessarily the case. Then you have the rotating part of the machine. So you can see this whole shaft that is moving through the center of the machine, mounted on the bearing, and onto the shaft you have field windings. So the entire shaft and the windings is known as the rotor, and rotor denotes that it is the part of the machine that physically moves. So an interesting case here. In our example before, remember we had the magnets, or rather the conductors inside a pair of magnet poles. And it was the conductors that were moving, and the magnets were stationary. So in this case, magnets are stationary. The rotating part of it is the current carrying conductor. In the case of, or in the language of the AC generator, the current carrying conductors are the armature, and the field windings are the magnets that were creating the magnetic field. And note that in this case, in the practical construction of the synchronous AC generators, the field windings are the ones that rotate, and the armature or the current carrying conductors are the ones that are stationary. The reason for that is, in order for you to tap off power from the machine, you have to have a way to connect it. If the current carrying conductors or the armature was rotating, you would need to have slip rings that would take off the power. So instead of that, practically the engineering convention is the part of the generator that is having heavier current, and the current carrying conductors are the whole purpose of the generator, are the ones that are stationary. So you have your armature being mounted on the stator in the case of your AC generator. In the case of the field, a bit more description. The field, the magnets that we have are not generally permanent magnets. The magnets in this case are electromagnets. So that is, you have a small amount of current that is being supplied to the windings inside the field, inside the rotor, and those then create the magnetic field that we are talking about. So instead of rotating the conductors within a magnetic field, you rotate the magnetic field within the conductors. So let's look a bit about the practical construction of your machine. So these two are cross sections of the rotor. We have disregarded the stator at the moment. So there are two possible constructions that you could have, which is salient poles, or you can have cylindrical or non-salient poles. Cylindrical. In the case of the salient pole, you have specific windings that are mounted onto a shaft, and you have poles with their magnetic fields being very clearly visible. In the case of the cylindrical windings, you can have one winding here going across to another winding there. This winding going across to that winding going. So they are distributed along the surface of the machine, okay? And that is why they are called cylindrical. The windings go around the machines along its surface. So from this point, they don't even go inside, as has been said. They go from one to the other along the surface of this side. Whereas you have your poles, the windings are mounted. You have a projection out of the rotor, and it is windings that are mounted along this side. And in cylindrical, they move from one side to the other along the surface of the cylinder. What's the reason for that? You then have this type of rotor. So is this rotor a salient pole or a cylindrical pole? What would we have? Just to see if you're awake, let's see the comments on the chat. So there are 30 of us. Give your opinion. Is that a salient or a cylindrical? This is actually a salient pole motor. Salient because you have these projections on the surface of the rotor. These projections form poles themselves. If you were to have a cylindrical rotor, you would have the windings going along the surface, and you would see them moving from one side to the other. And this shows an interesting characteristic of salient poles in that they have a large diameter, but their axis is very narrow but large diameter. What is the reason for this? Generally, there are various applications of cylindrical and salient pole. The salient pole windings, because of the inherent weakness of the salient pole itself, yeah, this is a projection. This whole thing is a projection out of the main shaft. And that, of course, comes with air resistance, imbalances, and so on. So this is only suitable for low speed applications. And by low speed applications, we mean the RPM must be less than 400 RPM. It cannot spin faster than that. This is suitable for high speed applications greater than 1000 RPM. Generally, things like hydro are very slow speed because the speed at which the water moves or hits the vanes is considered to be low. So in order for you to make maximum use of that, you would be inclined to use salient pole rotors. For everything else, gas turbine and the rest, you would have quite high speed cylindrical rotors. The reason for that is the windings would be embedded within a very robust cylindrical shape. So let's look at the principle of operation of the synchronous generator. So our aim is to produce three-phase AC that looks like that. Therefore, of course, you need to have three sets of windings. So there is your three sets of windings represented on the stator. In the case of the practical AC generator, the field winding is mounted onto the rotor. Now, your field winding, in this diagram, we've simplified it to just two poles, but as you saw on the salient pole rotor that we showed, there are very, very many that can be mounted. So you can have very many poles mounted on the same rotor. But for simplicity, let's have this one. In order for you to have your field rotating inside your machine with your north-south, the only way you can produce a north-south magnet using electricity is if you have DC current. So you have a DC excitation voltage that you apply to the generator through slip rings to the rotor. So if we go back to the construction, you will notice that we had slip rings here. So these slip rings are used to connect a DC supply. That DC supply provides a current that, when it passes through a coil inside the field, will then produce magnetism. So once you have that magnetism, you have your rotating magnetic field inside the rotor. Then, of course, by induction, you have windings on the stator, which then will have voltages induced in them that look like that. So you have your three sets of windings. Here we are calling them A, B, and C, into which your rotating magnetic field will induce a voltage. So that voltage has a three-phase characteristic or an AC characteristic, and it will have a frequency. And the frequency of the voltage is given by the number of poles. In this case, we have 2, but in a salient pole, you can have 20, 30, times the speed at which you are rotating the machine or rotating the rotor, divided by 120. So this is frequency, this is the number of poles, and this is the mechanical speed. Now, because of this relationship, the frequency is only determined by the number of poles and the magnetic speed. The value of DC that you apply is not relevant to the frequency. The amount of voltage that is produced is not relevant to the frequency. The frequency is only determined by how fast you spin the rotor, the number of poles that you have built into the rotor. And for this reason, that is where it gets its name of being a synchronous generator, because it maintains synchronicity with the mechanical speed at which it rotates. The number of poles will not change during operation. Once you've wound you've constructed the machine, the number of poles is fixed. However, the mechanical speed can change depending on what you want. If you want to rotate it at 1500 RPM, you can do so. If you want it to be 400, you can do so. The frequency that you produce will match the mechanical speed of the machine, and therefore you need, if you want to have a reliable speed at which or rather reliable frequency, you will need to maintain a reliable mechanical speed.